All right, good afternoon. Time for the quiz 2 review. So we should be well prepared for this. This shouldn't be too bad. So let's start off with the hardest question. So here's a forking question. Everyone's favorite. Yeah, I see some eyes turning. So let's consider the following code. It's valid to ask you to read code. So you have main, fork, 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 and then prints off what gets returned from every single fork. So some questions might be, some are too long for the quiz, so this should be actually harder than the quiz. So what's a reasonable set of outputs, assuming the initial process gets process ID 2, so that's the first process that executes from your terminal or whatever. And then some other questions might be, well, how many processes are there? What order of the prints? Is there any specific order of the prints? And what relationships do the processes have? So anyone want to answer any of these questions? Like maybe how many processes are there at the end of this? Or total? 7? 7, 8? 8? That was quick. Yeah, 8. So, and what would all their relationships be? Complicated. Yeah, well, let's go through it because this is going to be harder, probably harder than anything that would be on the quiz. So let's answer it in painstaking detail. Where's my button? All right, so we have this. Fork, 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 and then print with, I'm not going to write the print. So initially, we'll have process ID, let's call it 2. So 2 would be set off to execute main. We'll ignore, setting up the C standard library and all the other garbage. So process 2 would come in and call fork. So let's start drawing our tree. So we would have, let's put it smack dab in the middle, process ID 2. So it comes in, calls fork. It would create a child, new process, whatever. Let's give it a number so we can keep track of it. So let's assume it just gets process ID 3. So right after the fork, let's move this. So right after the fork.
Wait, sorry, these don't give 0 and 1.
Sorry?
I thought these either give 0 or 1.
Zeros or 1? No, PID is just a number.
Return 0 if it's the child, and return the PID of the child if it's the parent.
Yeah, so fork will return, the only difference is the return value. The child process is going to get a return value of 0, and the parent's going to get the process ID of the child. So in this case, right after the call to fork, we create a new process. It would be process, just give it a number. It would probably be process 3. So if we have PID 3, then in PID 2, what's the value of first? 3. It just created a child. We just said it was PID 3 for whatever reason, and I'll draw a line that indicates parent-child relationship. So in process ID 2, it gets returned a 3, so that's what first is. And then PID 3, what is first?
0.
Okay, cool, we're on the right track. So now they're both right after the call, right after the first fork. So can we say anything about the order that the processes get executed in? Nope. So up to the scheduler, let's, for argument's sake, just keep on going with process 2. So process 2, because they're all independent, would call fork again. Whoops. Process 2 calls fork again. Oh, geez. Oh, too big of an eraser. So process 2 calls fork again, and now it is right after the call to second, and it would have created another child. So it would have created PID, say 4, which would have been an exact clone of it at the time of the fork. So if it's an exact clone of it at the time of the fork, what is first equal to? 3, because it was 3 before the fork, so after the fork it's going to be 3. It just cloned it. It's an exact copy. So first stays the same, it's 3, and then what would second be in PID 4? 0, because this one was just created from that call to fork. In PID 2, what would second be? 4, because that was the child. And then we'd have, here, I'll move it down a tad. So that would be another child. Okay, well, we can't say anything about the order again. We have like 3 processes on the go. So let's just wrap up. Process 2. So I will clean this up. So 4 is right here, and so is 2. So if 2 calls fork again, it would create another child. It would probably be PID 5. What is the value of first for PID 5? 3. Why? It's just a copy of the parent. Okay. Well, what's the value of second in PID 5? 4. Why? Because it's still a copy of this parent, and that existed before. What is the value of third? 0, because it's the new child. In PID 2, what's the value of third? 5. Okay, cool. So then process ID 2, it's done. It could go ahead and call that print. We don't know what order it's going to be, so let's just get out of the way. So it would print first equals 3, second equals 4, third equals 5. And this would be from PID 2. So we'll just put that there so we know where it came from. And then PID 5 could also print. Could also reach the print statement. First would be 3, second would be 4, and third would be 0. So we can give that a little check mark, and now we can delete 2. So now we're assuming 2's done executing. Okay, well, let's assume the one that's furthest through and easiest, we just want to clear up space and get rid of them quick. So it's probably easier to argue about what happens to process ID 4. So process ID 4 is about to call fork again and set third. So if it calls fork, it will create another child, which would be the direct child of process 4 because it just called fork. So process 4 would spawn another process, probably PID 6, whoops. PID 6, what would the value of first be? 3, what would the value of second be? 0. What would the value of third be? Okay, in process ID 4 that just created it, what would the value of third be? 6. Cool, so now they're both done. We could print them off. First equals third, second equals 0, third equals 6. That's PID 4 taken care of. Then for PID 6, it would print off first equals 3, second equals 0, third equals 0. Okay, so they're all done. We can stop arguing about those. So now we have to argue about PID 3. So PID 3 has only just called the first fork and about to call the second fork. So as soon as it calls the second fork, again, creates a new child. It would be what? We're on PID 7 now. What would first be equal to? 0. What would second be equal to?
Should be 0.
0. It's the new created a child in 7. And then what would second be equal to in process ID 3? 7, because we just created it. Okay, so at this point now, we have 3 here and then 7 here. So let's just argue about 3 first. So 3 would create a new child. It would probably be PID 8. What would first be? 0. What would second be? 7. What would third be? 0. And in PID 3, what would third be? 8. So that's the process I just created. So now I can go ahead and finish these. So 3 would print first equals 0, second equals 7, third equals 8, and then 8 would go ahead and print first equals 0, second equals 7, third equals 0. So that would be check. So now we just have PID 7 to worry about. Where's my eraser? So we just have process ID 7 to worry about. That's just going to call fork again. We've done this like how many times? We've done it like 7 times now. One more time shouldn't hurt. So 7 calls fork, which creates probably PID 9. So what is first? 0 in PID 9. What is second? What is third? 0. And in PID 7, what is third? 7. Okay, 9. All right, so let's check that off. So 7 would print first equals 0, second equals 0, third equals 9. And then 9 would print off first equals 0, second equals 0, third equals 0. And would these specifically be in this order? No, they could be in any old order. If I wanted to print these in like somewhat specific order, what could I do? Sorry? Use a semaphore? I could, but I'd have to share them between processes, which we don't know how to do yet. No. Yeah. Wait. I could wait. So if we wanted to throw a wrench in this question, we could say, hey, is there any order if there's a wait? Which of course there would be. You would wait for your parent or wait for your child to exit. So the child would exit first. Yeah. Oh, PID 7? Oh, sorry. Second, sorry, that is correct. Sorry, second should be 7 in this case. Or wait, no, sorry. No, it's 0, yeah. It's 0 because it was a child. So it was created from the second call. Yeah, we did it right the first time. Yeah.
So the print order isn't like that necessarily that order because of the scheduling, but also like you're always going to create these 8 processes, but what variables they have don't necessarily have to be that either, right?
Yeah, so the PIDs would also be random, but their relationships would be the same. The tree would still look the same, so it'd still look like this no matter what, but the values are going to change. But they're going to change in a way that makes sense, where all the relationships are still the same.
Sorry, when your PID 3 splits into 7 and 8.
Sorry?
When your PID 3
Yeah.
splits into 7 and 8, does that mean like, so if you're 8, you assume 8 is not the parent, right?
So 3 spawned 7 and 8. I don't know what that arrow is. So 3 has 2 children.
So 3 is after the first 4,
3 gets created after the first fork, yes.
Then the second is the first child, 7, right?
Which one? 7?
I don't know, I'm not sure. Like, so 7, 8 is from the second and the third fork, right?
Yeah, so 8 was from the third fork.
Okay. Okay, I got it.
Yeah, so the original process has 3 direct children. The first process that process created has 2 direct children, and then one of them has 1 child, and then one of the other child of the original parent has 1 children, or 1 child. Does that make sense to everyone? So we count 8. We are in no particular order. If we wanted to make this a quiz question, we could throw in a weight and say what happens, and probably give you less forks. Yeah.
So what happens again if you call wait on the child if you have no children yourself?
Yeah, so that's a good question. We can just do that too. So where's the hell's my VM? So what about if I do something what about if I do something silly like this? Wait.
Wait, what about the final child? Like, those who don't have children, wait.
Sorry, the final child?
Like after you split, like the last child, like the children, like if they don't have any children, then how
Wait, sorry,
do
the
they
last
wait?
child gets produced first, right? That's the...
The last child gets produced first. What?
No, like, okay, your first splits 2, your second splits 2, your third splits 2, but then all the parents wait, so the child goes down, right? And then you basically all the waits is waits until the last child gets executed.
Kind of. Well, so if we have 3 waits here, that means every process after all the forks are done, they all call wait 3 times. By default, wait just waits on the first child to exit. So, oh, cool, free, nice. Where's my tablet? So if we have this and all of the processes call wait 3 times, how many processes actually have 3 children? 1. So we're gonna have a bunch of extra wait calls. Are you?
If you wait and you don't have a child, you just like not wait.
Yeah, so that's the good question is if you call wait and you don't have a child, well, what happens? Well, thankfully, they wrote out what happens. So if you just scroll to error, they give you a few errors. So wait can fail if this is a non-blocking call and the process isn't terminated yet. It will say it's not terminated. It will give you an error if the calling process does not have any unweighted children. So that means you don't have any children. So you'll just get an error. And you'll also get an error if that process does not exist or it's not a child. So you can't wait on a knit or something silly like that. You can only wait on your direct children. In some like old Unixes, you could wait on your grandchildren, but they quickly decided that was a horrible idea and stopped doing that. So only direct children.
Why are grandchildren not good to wait on?
Then you essentially you'll have races with waits, right? If 2 processes are trying to wait on one, it's like what? The first one that waits on it gets to see its value and the other one gets an error. And then you're synchronizing between processes and yeah, make our lives easier. So in this case, that code would actually work except for the first process that actually has 3 children, it would actually wait 3 times in return. For the other ones, it would just error. So
When it errors, it returns that way. Is wait a void function or?
wait's like a C function that returns the process ID that finished, 0 if there's still children, and it's non-blocking, and -1 if there's an error.
So it doesn't like stop the code, it just keeps returning error messages and you're just not dealing with it.
Yeah, it'd be return -1 each time and then set error no. So for the first parent, in this process ID 2 would actually wait on all of them, so it would definitely go last. So there you'd get some type of order here. So it would definitely go last, and like process ID 3 that has 2 children, it would make sure that 7 and 8 print before it, but the, sorry?
7, 8, and 9.
Well, 7, 8 directly, and then 9 because it's a child of 7.
Right.
But the third wait call would return an error because it's our children at that point. But you would get some type of order if we put in wait. Okay, any questions about that? So we pretty much answered everything. Good, reasonable output. Not too bad. So fork sucks the first time you saw it, but we've seen it like a few lectures now, so it shouldn't be too bad. All right, well, let's graduate and do a threading question. So this is saying if you have a global variable int I and 3 threads, before it executes the value of I is 0, and then you have 3 threads, so 2 are going to execute I++, 1 executes I-, and then the question is, what are all the possible values of I after all the threads execute? So I'll give you a second to think about that, and then we can go over it. Yeah, int's just normal. No, yeah, unsigned in. No, signed in, sorry. It's signed. Yeah. Yeah, int's just a normal signed integer. I mean, if it couldn't instead of -1, it would be max.
Wait, are there locks?
Nope. So this doesn't have any locks, so I guess first question is there a data race? Very, very much so. Every single thread is reading and writing. I really like the fact that they're excavating beside us. Makes things interesting. All right, so is it possible that I is 1 at the end of this? Yeah, which is what you would expect if you just had a single thread. So 0 to 1, 2, then down to 1. Could it be 2 at the end of this? Could it be 0 at the end of this? Could it be -1 at the end of this? Yes?
Wait, sorry, why would you have to again? Doesn't the thread always execute?
You don't know the order. Okay, so we think it can it be -2? Can it be 3? Okay. Okay. So I guess, yeah, so the question might be, well, how do I argue about it? So you're wondering how it is 2? So let's go over it. So each thread will have these kind of 3 instructions: read from memory, then increment or decrement, and then write to memory. So if initially I is 0, let's see. Someone give me an interleaving of threads that gives me the value 2 at the end of this. Sorry? So tell me how I could get a 2 out of this. Has everyone agreed that I could get a 2? So I hear thread 1 starts, read, it would read a 0, then it would inc it to a 1. Now just write it, okay. So I write it out. Now I is equal to 1. Thread 3 reads it, so it would read a 1.
Wait, it's not good decrement?
I don't know. So someone has to tell me what to do.
It should be
Thread 2 reads. Okay, so this is our alternate timeline. So thread 2 reads. So it would read a 1. Actually, no, screw it, I'll just delete it. So we said thread 2 reads instead, okay? So thread 2 reads the 1. Sorry? Yeah, so we didn't actually need to do that. At this point, it doesn't matter which one reads first. They're both going to read the same value. It doesn't really matter what one reads for. Yeah, so at this point, the only difference is who actually writes first. So thread 3 would decrement, so it would go to 0. So if I want 2 at the end of this, should thread 3 continue to execute? Yeah, so it would write out 0, so now I is equal to 0. But now thread 2 is the only thread that has any instructions left. It read a 1, so it would increment it to a 2, and then it would write out I, and now I is equal to 2 when we're done. And then we also have the case here. We can see how we would get 0 at the end of this. So we would get 0 at the end of this if we just kind of flip these around. So if thread 3 came back later and wrote, so if it looked like this, then we would get 0. So it just depends on the order they wrote. And so the idea of this is they just read some stale data. All right. Well, I guess for practice, so the most difficult scenario might be, how do I get a -1? Yeah.
Thread 3 can read the 0.
Thread 3 reads I, which is a 0, okay?
And then all thread 2 and thread 1 activate whatever order they do their stuff.
Okay, I can,
And they both write, yeah.
I just deck. Yeah, so now thread 3 wants to write out a -1, and then thread 1 can go ahead and execute, read that 0. It still hasn't been updated. It could inc, which now is a 1. Then it would write out the 1. So now the global I is equal to 1. Thread 2 could come along, read 1, inc it. So now it's a 2. Then it would write 2. So now I equals 2. But thread 3 still has its write left to do. So it would write -1. And now I equals -1 at the end of this. So it's just a whole bunch of different options. But no matter what, each thread individually executes in order. You just don't know anything between them. And that's the only kind of challenge here. Yeah. Any questions about that? Yeah, stark difference between the morning class. We're actually awake now. This is great.
Wait, it can't be 0 too.
Yep.
I just want to start with 1 and then start, okay.
Yeah, we had 0 and just switch the order of the writes at the end of the 2 example. And then to get the value 1, you just execute one thread till it's done, another thread till it's done, and then the third thread till it's done. And that's kind of what you would expect anyways. All right, any questions on that? We're good. We identified our data race. We came up with a bunch of different answers. Cough. All right, cool. No questions at all about threads? Yeah.
So is it mostly like forking and threads that we're focused on, or is it also like monitors and cyclers and stuff?
Monitors are just mutexes that are made for you. They're kind of lame. Condition variables are decent. So let's go. Okay, well, let's whirlwind through everything and go back and I guess maybe visit condition variables or anything else. So essentially, I'll just go through the summary of all of the lectures and then point out what's important. So, Unix system calls. They have a parent-child relationship. That's good to know. Creating new processes with fork. I mean, we just spent a good time going over a fork example. If you're betting, there's probably a fork question on the quiz. And then after the fork, both processes are exactly the same. Only difference is their PID is different, and we went over a whole bunch of different scenarios where we actually created 8 processes. Well, we had 1 process, so we created 7. So that's the only difference. That's with fork. It's an exact copy. Hopefully we've seen it enough time by now that it makes sense. The first time it probably made no sense. Hopefully now it makes a bit more sense. And then, of course, we have the scheduler that we can't say the order anything runs in, and that's been true the entire time. So you're responsible for managing those processes, so the operating system makes sure that there's that strict parent-child relationship. So we saw zombie processes that are processes that have exited, but no one's waited on them yet, so they just have resources chilling around that the kernel can't delete yet. And then we saw orphan processes because a parent process can exit before a child. There's no way to kind of restrict that. And with an orphan process, it'll just get reparented, likely to init, and that will then clean it up. So we kind of know what init does. It just sits there and waits over and over and over and over again to claim any children and clean them up. So for quiz 2, section 1 doesn't actually know that much about zombie processes and orphan processes, but they have encountered wait. So wait just waits for the first child to actually exit by default, or you could wait on a specific child. And that will kind of ensure some order because you're waiting for one of your children to die. Any questions about wait or any of that? Yep.
There's no order to it at all. It's literally just the first child.
Yeah, if you call wait without a specific PID, it's the first child that dies. Which is annoying because for thread join, there's no like equivalent of that because for thread join, we have to wait on a specific thread. Yeah.
So if the process has a child and the wait is blocked, but it doesn't have a child,
Then it's an error.
then it's not blocked.
Well, there's nothing to block on, it's just an error.
But it will continue if you don't care about it.
Yeah, he'll just return an error, and if you ignore it, you ignore it. So it's like programming in Java, right? You just ignore the error and carry on, and bad things happen.
So if you want to don't wait for all your things, children to die, you just keep following the wait and then until it returns error.
Yeah, so if you are a process, well, you can only wait on your direct children. So if you create them, you should know how many you have. So then you should wait the appropriate number of times. If you're a init, you don't know how many children you have because you keep adopting them. So that's why init is basically, it doesn't just do wait until there's an error. It would just do while true, wait. Yeah.
So the wait waits on the first child that exits, it reads that exit code, and then it kind of, the OS clears up the resources of the child that exited, right?
Yeah. No? Well, but it doesn't have any data races or anything because the kernel programmers are good. But it's not like atomic. Yeah.
But you said join, you have to wait on a specific PID?
A thread. Because that was like pthread join,
Oh, yeah.
which was kind of like wait, but for threads.
But you can't just wait for the next one.
Yep. yeah, just, it's their annoying API. All right, any more questions about weight? Okay, so we saw like IPC, like read and write, redirecting file descriptors, which was cool, signals, which was really cool, and that you encountered in lab 3. And signals were just like interrupts. This really isn't covered on the quiz because the other sections haven't played around with file descriptors and they haven't had as much fun as us. So don't have to worry about this. There might be like a little bit about signals, but honestly wouldn't worry about this because section 1 didn't really do it. Then we talked about threads. Oh God, threads are the best. So we saw threads, related them to processes. They're lighter weight because they just share memory by default. They're all in the same address space as the process. So all the memory is shared. The only thing that is private to you are your registers and your stack. Yep.
When you exec D and you transform into a different program or whatever,
Mm-hmm.
how do you get to decide at all how much memory, like actual physical memory, the operating system allocates you, or do you just always assume that your virtual memory is infinite? Like what if a process needs more memory than another process?
Yeah, so you don't even have to exec for that.
But like when a process gets created, I mean, when a process gets created, how much memory is it allocated?
So when a process gets created, as part of like the executable file format, it'll say how much memory it initially needs, and then the kernel will just set that aside for that process and make sure it's available when it's executed.
Okay.
And if it doesn't have enough memory, it's going to go not launching that out of memory. And then while the process is running, there's system calls like that BRK thing we saw that essentially just extends the heap. And you just essentially just ask the kernel for memory. And for the threading example, last time we ran out of memory. That's whenever we had too many bank accounts. And then then the kernel was like, malloc's okay, but then when we tried to actually read or write memory that was past our limit, it just killed the process straight up.
Because if you had done that, you would have been reading outside of the virtual memory you didn't allocate, and you would have accessed some other program.
Well, we were accessing within our virtual memory, but we didn't have enough physical memory on the machine.
Oh, okay.
So the kernel was just like, yeah, bye. But the allocation was fine. Malloc was returned success and gave us a memory address.
So how does malloc return success? Isn't the whole point of malloc like make sure you have that memory?
Yeah, but malloc just uses the kernel system calls, and if the kernel lies to it, what can it do?
Oh, so, okay.
And we'll see virtual memory after this. And yeah, whenever you start a process too, it just has a single thread. That's it, single kernel thread. Yeah, you should know a bit about exec.ve. It just transforms the process. That's it. Doesn't create a new process or do anything special. Just transforms it, reinitializes it, loads everything. Why might it have to reinitialize everything if the only way to create a new process is a fork, and then it would exec to start a new process? Anyone guess why it would probably want to reinitialize the memory and everything like that?
The program counter is the same as the one called exec.de.
Yes, but that would reinitialize the registers, not the memory. So imagine if you had, your bank account open and something like that, and then that forked and exec. Well, you probably don't want that process to be able to read your memory. So
Oh.
probably want to just wipe that out and,
So for security reasons, it's clearing
yeah, to make sure everything's independent if you don't want. So exec will clear everything and reinitialize everything for you. Okay, any other questions? Okay. So we saw there's both processes and kernel threads for parallelization. We kind of talked about the relationship between kernel threads to user threads for the purpose. So your lab was all user threads, P threads were all kernel threads, and really don't worry about anything in between. The major thing here was that now we have threads all in the same address space, So we have synchronization issues, which are everyone's favorite. So we saw one easy way to get rid of data races was have a critical section where we had a mutex or a spin lock that ensures mutual exclusion, so only one thread can execute that critical section at a time. And that prevents a deadlock because a deadlock needs two concurrent accesses with one being a write. So if we only have one thread in one block of code at any given time, there's no data races because there's only one thread accessing it. So we saw that. You don't really have to worry about how to implement the locks. The quizzes are more how to use them because the labs were how to implement them. And read-write lock, the other section does not know. So don't worry about read-write lock. But it's pretty much just for performance reasons. Then we saw center fors. So we saw mutual exclusion with mutexes and center fors, which were just a value. And then you can increment it using post. Yeah, it's called post. You can decrement it using wait, and it will just block if that value is 0 and wait for it to increase to at least 1, so it can decrement and not go below 0. So it will just work like that. You can use them to ensure some type of order, but this is mostly ordering. You can use the center for as a lock, like we kind of saw, but you might use them for ordering, and in which case there's still potential for data races, which you still have to solve. And of course, you can use mutexes. So then we saw more advanced locking, like the condition variables. They were kind of clearer for more complex condition signaling. We saw like locking granularity in that parallelization example, like how much code our lock was blocking and how many locks we had affected how fast it ran. And when we had less accounts, there was more locks getting in the way of each other and it was slower. But again, you must prevent deadlocks if you have multiple locks going on and be able to identify cases where deadlocks could happen. Okay, so let's quickly, so probably the hardest thing from that was that producer-consumer example. So let's read it again. So ignore this center for because it's just keeping track of how many things get produced and consumed. So if we have something like this, does everyone kind of understand why this is written as it's written? So remember, this was like a producer-consumer where we had a buffer with a certain amount of slots, and we didn't want to miss any data. So if every slot was filled, we wanted to stop our producers from producing any more data until a consumer came along and it freed up at least one slot. Yep.
So the pthread condition wait is like a blocking call until a signal has been set, right, from pthread condition signal.
Yeah, so pthread condition wait essentially will atomically put yourself in a queue called has filled and put yourself to sleep until someone signals you or wakes you up with a broadcast.
Why is there the CD mutex in there?
So the lock has to be held when you call wait, and whenever it returns from wait, it also still has the lock.
But while it's blocking, it doesn't.
Yeah, while it's blocking, so atomically it would add itself to the queue and give up the lock and then block itself. And then later when something signals it, before it returns from the wait, it would grab the lock again, which is important. So in this case, if if all the slots are filled, it puts itself in a queue that's essentially waiting for at least one filled slot and then doing this over and over again. Why would it want to do it over and over again? Yeah, so another thread, when I woke up, it's going to grab the lock again. If something, what am I waiting for? Yeah, if something filled a slot and then signaled me, by the time I wake up, does that mean that the slot's still filled? No, so I might wake up from the condition variable, and that condition might not be true anymore. It might have been true at the time of the signal was sent, but by the time I wake up, that doesn't mean it's still true. So if I replace this while with like an if or something and didn't check it again, I might be screwed. And outside of the scope of this course, for some operating systems, wait just might like randomly return to you. But assume for the purposes of this course, wait just doesn't randomly return to you. But with some, so if I change it to this, something very bad could happen, right? All right, any other questions? Yeah.
So the signal isn't actually, when it's waking it up, it's just putting it at the end of the record queue, right?
When it's woken up, it like removes itself from the queue
From the wake queue and puts itself.
and then grabs the lock again.
But like it doesn't immediately run, right? It's like it's in.
No, because it has to grab the lock again before it returns, and you don't know when that's going to happen.
I see. Okay.
Yep.
You have to grab the lock again because this essentially is a critical section.
Yeah, this essentially is critical section, and that like queue also has to be protected, and it would be in a critical section.
Critical section, it waits, so it exits the critical section. When it gets it back, it re-enters.
Yeah, and it would be in a critical section too because it's waiting on some condition, and you don't want data races on your condition either. So you're going to have a critical section anyway, so it may as well take advantage of it. Yeah.
So when you said that like adding itself to the wake queue and blocking it, like returning lock, that's all atomic. So is there like a mutex within that function that ensures that, or how is that? How is the atomic nature of that function?
You implemented one, right?
So it was using internal. Like, was it like turning off interrupts? Is that the way it's doing?
So turning off interrupts only works if that's the only source of it. It would probably use something like an internal lock, like how we implemented the blocking mutex. Probably do something similar to that. Because you're allowed to just turn off interrupts, and that essentially acts as, turning off interrupts for lab 3 essentially is a lock, and then enabling them again is unlock.
And that only works for like single core, right?
Yeah, that only works for single core, and if interrupts are your only source of concurrency.
How could you?
So in the hardware, like a real interrupt, you have no control over when it comes in. And like if that went to your process and messed up your process, then you have no control over it. If you're the kernel, you can do that though. But that also might just be too slow. If you just disable interrupts globally, that might not be a great idea. Right, so we'll go over it quickly. So Asha and I will be on Discord. I also have office hours after this, although forewarned, if you follow me back to my office, I need help flipping my desk back over. Yeah, long story. So Asha and I will be on Discord during it. If you want to direct message us, again, Discord will be muted, no talking to each other, blah, blah, blah. We'll announce anything problems there are, but hopefully there will be none. There's going to be 2 true false, 2 multiple choice, which by the looks of the time commitment aren't really multiple choice, and 2 short answer that are mostly like free form. So, yeah, which means they're not really multiple choice. So, 1 minute each for true false, and then 10 minutes each for the multiple choice. So, you can probably guess what they are, given today's review. And there probably won't be any issues because you will have like 16 different options. So one of them is going to be right. Yeah.
Is it an actual multiple choice or is it a select all that are?
It's an actual multiple choice. But there's 16 choices.
Wait, sorry, I don't understand. Can you select one of these wrong?
What? Yeah, we have to battle that when it comes. But we didn't do multiple answer because the Quarkus grading scheme is so stupid with it that like it varies wildly depending on how many right answers there are. So there's like 2 right answers and it's worth 4 marks. Each of those are worth 2 points. And then if you select the wrong one, it's -2. So you pretty much get 0 or full marks anyways.
Right.
So if you choose 1 right, 1 wrong, you get 0. Yeah, so it's probably something like a data race or something like that. So read it carefully and reason about it. You have a lot of time to go back over it. All right. Any other questions? Yeah. I had to fix it. I flipped it myself. It was intentional. All right. Well, remember, I'm pulling for you.